It's been a while since we solved questions on permutation and combination. I thought we would solve some questions to brush up on those concepts. Are you ready?
Yes, I am ready.
But these questions would warrant your basic knowledge of all the fundamental concepts of the chapter. I hope you remember all the basic formulae and stuff. Let's solve our first question. There are 4 boxes each containing n balls. The first box contains n identical red balls, the second box contains n identical blue balls, the third box contains n identical black balls, and the fourth box contains n distinct balls. The number of ways to select n balls from these 4 n balls is. Here we have 4 boxes each containing n balls. Totally we have 4 n balls. From these 4 n balls we have to select n balls. In how many ways can this be done?
Just selection. Is it for NCN?
That is only when all the 4 n balls are distinct. But here some of the balls are identical. From identical balls it doesn't matter which ball is selected because all the balls look alike. Only what matters is the number of balls selected. Right? Here one set of identical objects, another set of identical objects, and some balls are distinct. From this mixed group of identical and distinct objects we have to select n balls. In how many ways can this be done?
Then is it n plus 1 cubed multiplied by 2 to the power n?
That is only when you don't have a specific number of objects to be selected. Suppose you are free to select any number of objects. Then from the first set of n identical objects we can have n plus 1 selections, again n plus 1, again n plus 1, and from the last set of n distinct objects we can have 2 to the power n selections. But that is only when the number of objects to be selected is not fixed. But here we only have to select n objects from the total 4n objects. So the number of objects to be selected is a fixed number n. Then we have to do it in a different way. Suppose we are selecting some objects from the first set of n identical objects. Which objects are selected? Does it matter? Only what matters is the number of objects selected, because all the objects are identical. Which object doesn't matter. How many objects? Only that matters. Suppose x objects are selected from the first box, and y from the next, and z from the next, and from the last box we have selected r objects. But which r objects are selected? That matters here. Here only number matters. There which objects are selected, because all those objects are distinct there. So suppose we have n objects, so NCR we have to select also, right? Which r objects are selected. Now we have to consider many cases. Depending upon what the value of r is, we will consider many cases. Suppose we are selecting no objects from the last set of identical or distinct objects, right? R is 0. So that is the first case. Let us consider the first case. R is 0. That means no object is selected from the distinct object. That means all these objects, n objects are selected from these boxes only. So that means this total x plus y plus z, that must be equal to total n, right? Now we have to write the number of solutions. 0 objects are selected. That means from the n, 0 objects. So how many ways can this be done? So the number of solutions, we are writing the number of solutions here, which is nc0. 0 objects selected. Now we have to write the number of solutions of this equation, right? Number of non-negative integral solutions of this equation. So that is the formula. So this one, n plus r minus 1 c r minus 1. Number of variables r is 3. So n is this one. So n plus 3 minus 1 c 3 minus 1. That is same as this multiplied by, so the number of solutions of this is n plus 2 c2, right? So that's all. That is the first case only. Now we will consider the next case where r is 1. If r is 1, one object is already selected. That means from the remaining boxes we have to select only n minus 1 object. So that means our new equation here is x plus y plus z equals n minus 1. Now we will write the number of solutions in this case. Now here nc0, now nc1 here, multiplied by the number of solutions of this n minus 1 plus 3 minus 1 c3 minus 1. So that is same as n plus 1 c2. So we can keep doing this. The last case is r is n itself. That means all the balls are selected from that last box only. That means this equation will become x plus y plus z equals 0, because all the balls are already selected, so nothing is to be selected from the remaining boxes. So how many solutions are there in this? We have a n, so that means ncn. Okay, so that is ncn multiplied by, so 0. So how many solutions are there? 0 plus 3 minus 1 c3 minus 1, that is 2c2, or it is just one solution, right? So this is 2c2. Okay, so that's all. Now we have to add all these cases. That's all. So these are the different cases. Now we have to add this to get our required answer. So what is that solution? So multiply that. So nc0 multiplied by n plus 2c2 plus the next one nc1 multiplied by n plus 1 c2 etc. right? So n plus 1 terms are there totally. We will add this. But how to add these terms? We have to use some idea of the binomial theorem. See, nc0, nc1, nc2, these are directly the binomial coefficients. But these are different. Here the values are different. N plus 2 and this is n plus 1. Next to n minus 1 etc. So these values are decreasing. But these are constant, right? 2 here. So when you say 2 here, that is the coefficient of x square in the expansion of 1 plus x to the power n plus 2. This is coefficient of the same x square only in the expansion of 1 plus x to the power n plus 1. So from each term we only find the coefficient of x square. So what we find essentially is the coefficient of x square. In first term is nc0. This is 1 plus x to the power n plus 2. Next term is same coefficient of x square, nc1 multiplied by 1 plus x to the power n plus 1 etc. So these are like again binomial terms only, right? nc0, suppose this is y, nc0 y to the power n plus 2, nc1 y to the power n plus 1. If you want, you can take out 1 plus x square. If you take out 1 plus x square multiplied by, you will get nc0 multiplied by 1 plus x to the power n plus nc1 1 plus x to the power n minus 1. Okay, so these are the binomial terms. Alright, it's like nc0 y to the power n plus nc1 y to the power n minus 1 etc. So that is the expansion of y plus 1 to the power n, right? Y plus 1 to the power n, that is only nc1 y to the power n etc. Alright, so that means, so this is simply the expansion of, this is the expansion of 1 plus x plus 1. Okay, 1 plus x plus 1 to the power n, right? So 1 plus x to the power n. Next nc1, 1 plus x to the power n minus 1 etc. Alright, so that's all. So this is same as 1 plus x square, 1 plus x square. So that can be written as 1 plus 2x plus x square multiplied by, this is 2 plus x to the power 2 plus x to the power n. From this we have to find the coefficient of x square. How to find the coefficient of x square? 1 multiplied by x square term. But already 2x multiplied by just x term, because already x is there, we want to get the coefficient of x. Next x square multiplied by the constant term, right? From each term, multiply each term with this and find the coefficient. First 1 multiplied by the x square coefficient. What is x square coefficient? That is the third term, right? So that is nc2, right? nc2 2 to the power n minus 2 x square 1. So x square term we want. So that means it is nc2 2 to the power n minus 2. Next 2x. So that means 2 multiplied by, x is already there, we only need the coefficient of x. What is the coefficient of x? That is the second term, right? So that is nc1 2 to the power n minus 1. So nc1 2 to the power n minus 1. And then x square multiplied by constant term. So x square multiplied by constant term here is 2 to the power n only, the first term itself. So 2 to the power n. So that's also, this is our required answer, but we have to simplify this. We can take out the common factor. So what is the common factor here? So we can take out 2 to the power n minus 2. If we take out 2 to the power n minus 2, it is nc2. But nc2 can be written as n minus 1 divided by 2 plus, and 2 to the power n minus 2 is taken out. So that means the 2 times 2. So that is 4n plus 2 to the power n minus 2 is taken. So that means it is just a 4. So let's simplify this further. So this 2 we can divide. So it is 2 to the power n minus 3. So that is n square. 2 multiplied by 4n. So that is 8n minus n. So that is plus 7n. Plus 2 multiplied by 4. So that is 8. So that's all. So this is the required answer, right? So this is the number of ways to select n balls from these 4n balls with that condition, right? Because some balls are identical. So from identical balls, only what matters is the number of balls selected, right? So number of balls, so number of solutions of this equation. But the last set of balls, so they are not identical, they are distinct. So we are selecting, right? We have to count, right? Which objects are selected. So let us first take the number of cases, right? So 0 object selected, 1 object selected. So we have to consider different cases, then add all these cases, we get our required answer 2 to the power n minus 3, n square plus 7n plus 8. Okay. We can also get this series by another method. We've considered various cases, right? Now let us write the first case. So that is NC0. That means 0 objects selected from the set of n distinct objects. Now plus the next case. So that is 1 object is selected, NC1. Multiply this by x to the power 1. See, the power of x represents the number of objects selected from the last set of distinct objects. So x to the power n. So 1 object selected. So that can be selected in NC1 ways. Similarly, the next term. So that is, suppose 2 objects are selected, NC2. That means x square. The power here again is the number of objects selected. So this is the number of ways to select those 2 objects, right? So etc. Okay. So till the last value n. Now multiplied by, now from the identical objects. When you say identical objects, here we need not select the object. How many objects are selected? Only that matters. That means suppose you are selecting 0 objects, so x to the power 0, or 1 object, so x to the power 1, or 2 objects, x square, so etc. So to the power 3, because 3 sets of identical objects. Alright, yes. Now here we are not multiplying NC1, NC2 because we need not select. Okay, once the number is fixed, that's all. Alright, from this what we have to find is the total. The total is n number of balls to be selected. That means from this what we have to find is the coefficient of x to the power n is what we need to find in this product. Alright, let us find this product. So this is what, this is the binomial expansion, right? 1 plus x to the power n, or we need not write it, we will leave it as it is. So this is nc0 plus nc1x plus nc2x square plus etc. This is a simple geometric series, right? Sum of geometric series. So how to find? So that is a divided by 1 minus r. So that is 1 divided by 1 minus x, or we can write it as 1 minus x to the power minus 1, here power 3. So that's all. From this we have to find the coefficient of x to the power n. So each term should be multiplied by this one. Right, each term you multiply with that and find the coefficient of x to the power n. NC0 multiplied by x to the power n coefficient. What is the coefficient of x to the power n in this expression? So that is the formula you have to remember. In the expansion 1 minus x to the power minus r, the coefficient of x to the power n is n plus r minus 1 c r minus 1. So r here is minus 3. That means the required coefficient is nc0 multiplied by coefficient of x to the power n. So that is n plus r here is 3. 3 minus 1 c 3 minus 1 plus next term. Next term is nc1 multiplied by, already we have x here, so we only need x to the power n minus 1. So what is the coefficient of x to the power n minus 1? Again same formula, this time n minus 1 plus 3 minus 1 c 3 minus 1 plus etc. Many more terms are there, but if you observe, so same expression here, right? nc0, this is n plus 2 c2, and this is n c1, n plus 1 c2, etc. Alright, so the same expression we can get by considering different cases like the previous method, or we can also use this coefficient method, right? So usually we consider only this thing, right? Write the powers of x as the number of values, number of objects selected. Okay, but here in addition to that, not only the number, which object selected, so that means each term is multiplied by that selection also, nc1, nc2, etc. In this product we have to find the coefficient of x to the power n, right? N is the total number of objects to be selected, so find the coefficient of x to the power n in this expression. So that is the required answer. Once you get the series either by this method or considering different cases, but the value of this series is found only by this method, alright, using that binomial terms. So that's all. So that is the required answer. Okay. There are 4 boxes each containing n balls. The first box contains n identical red balls. The second box contains n identical blue balls. The third and the fourth box contain n distinct balls each. The number of ways to select n balls from these 4 n balls is. This question is for you to do. It is similar to the last question. Here, instead of 3 sets of identical objects, we only have 2 sets of identical objects and 2 sets of distinct objects, but you almost have to follow the same steps that we used in the last question. Just like the last one, this one is also heavily dependent on the concepts of binomial theorem, but that is for you to think about.
Can we take the value of n to be a particular number like 1 or 2?
Yes, you can take the value of n to be as small as 1 and verify the options. If you are lucky, only one option satisfies, you are through. But the purpose of the question is not that. I could have as well given a number as big as 100 or 200 instead of just n. So that method doesn't work always, but you can narrow down the option. If you're lucky, maybe in your exam it might work out, right? But here you are supposed to find the answer for a more general case n. Okay? Consider 4 boxes where each box contains 3 red balls and 2 blue balls. Assume that all 20 balls are distinct. In how many ways can 10 balls be chosen from these 4 boxes so that from each box at least 1 red ball and 1 blue ball are chosen? I've already discussed this question here. By method, considering all the different cases, you can check that out here. One from each box, that means only 2 more balls have to be selected. For these 2 balls, we have to consider many cases, right? So from which box? Now, to make things more complicated, we're going to use another method to do this question.
That method seems to be simple enough. Don't complicate it.
If you make some changes in the question, some methods might not work. Let's learn another method. It could be handy sometimes. See here, we have to select balls from the boxes. So how many balls are selected from which box? So that matters. Not only that, which ball also matters here because all the balls are distinct, not identical. Suppose we are selecting x1 balls from the first box, only red ball. x1 red balls are selected. Alright. Similarly, y1 blue balls are selected from the first box. Similarly, x2 red balls from the second box, and then y2 blue balls from the second box, etc. Right? Now we have to count the number of possible ways of selecting this. Right? First, let us count the number. Right? That means x1 plus x2 plus x3 plus x4 plus y1 plus y2 plus y3 plus y4. Right? This total must be equal to 10 because total number of balls selected is 10. So this is the equation. So x1 plus x2 plus x3 plus x4. This is the total number of red balls selected. Only red balls from these 4 boxes. Similarly, the blue balls. So that is y1 plus y2 plus y3 plus y4. So this total equals 10. Right? So this we have to find the number of solutions. Now what are the values x1 can take? x1 can take value 1, 2 or 3 because minimum 1 ball has to be selected. So minimum 1 and 2, 3 maximum. So now we write the possible values of x1 as powers of x, right? Now then we are going to find the coefficient of x to the power 10, which is the total. So x to the power 1 plus x square plus x cube. These are the 3 possible values of x1, 1, 2 and 3. And similarly for this variable x2, same value, right? 1, 2 and 3. Similarly for x3 and x4, that means this whole thing to the power 4. Now multiplied by similarly y1, y2, y3, y4. All the variables take the same set of values, like 1 or 2, right? Only 2 values. So either it takes values 1, that means x to the power 1, plus or it can take value 2, x square, right? To the power 4 because 4 variables are there. Alright, yes. Now from this we find the coefficient of x to the power 10. That would be the answer if all the balls are identical. But here all the balls are distinct. That means not only the number of balls selected, also which ball is selected, that also matters. So for example, here 1 ball is selected from the first box, for example. Then which ball is selected? You have to select that ball, right? So there are 3 possibilities, right? There are 3 balls out of which 1 ball is selected. So that means this should be multiplied by 3c1 also. Usually when the balls are identical, we will simply write this expression. From that you find the coefficient. Now suppose here 2 balls are selected. Which 2 balls from the 3 balls? So that means you have to multiply this by 3c2. Similarly 3 balls are selected. That means which 3 balls? 3c3. Okay, and here 1 ball is selected. That means 2c1 because 2 blue balls from the 2 balls 1 ball is selected. Similarly here 2, so 2c2. From this what we have to find? The coefficient of, you have to find the coefficient of the total, that is 10. So x to the power 10 in this expression, that will give you our required answer, right? Let's simplify this first. So 3c1 is okay, you can take 1x out, so that will become x to the power 4 and 3c1, so that is 3 plus 3c2 is 3 again, 3x plus 3c3 is 1, so that is x square multiplied by, so here also we can take x out, so x to the power 4, so 2c1 is 2, so 2 plus x to the power 4. Now we want coefficient of x to the power 10 in this, but already we have x to the power 4, that means x to the power 8, so divide by x to the power 8. So what we need is the coefficient of x to the power 2 only, because x to the power 8 is there, so you divide by that, x square only we want from this multiplication. Let us multiply this. Alright, so let us simplify this. So if you multiply 3 multiplied by 2, so that is 6 plus and x term, so 3x multiplied by 2, that is 6x, and 3 multiplied by x, so that is 3x, so that means total we have 5x, okay, x term. Similarly we will write x square term. So x square multiplied by constant will give you x square, right? 2x square, and x multiplied by x, 2x square plus 3x square, that is 5x square. Similarly, x cube term, x square multiplied by x, that is x cube. So x cube to the power 4, right? From this we have to find the coefficient of x square, right? Yes. So x term, so 3 multiplied by x, so that is 3x, plus 2 multiplied by 3, that is 6. Alright, it means 3x plus 6x, so that is 9x, not 5x. So this is 9. Alright, so this is the expression. From this we have to find the coefficient of x square, right? Yes. Now what we do, so we can simply write it as 6 plus 9x plus 5x square, right, to the power 4, right? We can ignore this x cube, right, because we only need the coefficient of x square.
Can we simply ignore x cubed?
We only need x square term. Or if you square this, you may get x square term. A constant term multiplied by x square will give you x square term, but x cube will never give you x square term. If you raise any higher power, that power will be bigger than x square anyway. So now if you multiply this with any of these terms, you will never get x square, right? So this term is not required. Or even if you consider this term, so you will get the same answer, right? So any higher powers, right? Because we need only x square, so any higher powers, x cube, x to the power 4, etc. can be ignored, right? Yes. So this is the expression. From this you have to find the coefficient of x square, but this is not a binomial expression, right? This is multinomial, right? Because there are 3 terms, so you have to use the concept of multinomial, right? What is the general term of a multinomial expression? So that is this one, 4 factorial divided by this 4 factorial divided by 3 variables are there, the p factorial, q factorial, r factorial, this 6 to the power p, and then 9x to the power q, and 5x square per r. Alright, so this is the general term of the binomial expression, where p plus q plus r is the total 4. Alright, from this you have to find the coefficient of x square. Let's simplify this first. So 4 factorial divided by p factorial, q factorial, r factorial. This is 6 to the power p, 9 power q, and 5 to the r, and then x to the power q plus 2r. But we want x square term, which means this q plus 2r must be equal to 2. What are the possibilities? Let us count all the cases. So q plus 2r equals 2. That means what are the possible values of q and r? And we can also write the value of p. See, q plus 2r is 2, which means q is 2. That is possible. And r is 0. If q is 2, r must be 0, right? And then what is p? The total is 4. P plus q plus r is 4. That is the total. So that means p is also 2. Now the next case. Q plus 2r is 2, q may be 0 and r is 1, so that is possible, and the total is 4, that means this is 3. So these are the only possible cases, right? So these are the 2 combinations which will give you our x square coefficient. Let us substitute the first case, right? 2, 2, 0. So p is 2, q is 2, r is 0. So that means the 2 coefficients are 4 factorial divided by 2 factorial, 2 factorial, 0 factorial, and then 6 to the power p. So that is 6 to the power 2, and then 9 to the power q square, and then 5 to the power 0, alright, plus next term 4 factorial divided by 3 factorial, 0 factorial, 1 factorial multiplied by 6, 9, 5. So 6 to the power 3, 9 to the power 0, and 5. Now let's simplify this to get our required answer, right? So here we can take out some common factor. So 6 square can be taken out, multiplied by, this is 4 factorial, that is okay, so we can just take 2 out, so it will become, so 6 square is taken out, so this is 4 factorial by 4, so that is 6, right? So 6, 2 is taken out, so that means it is 3, 3 multiplied by 9 square, 81, 243, plus now this 6 multiplied by, okay, so this is 2, so that is 12 multiplied by 560, so that means this is 72 multiplied by, this is 303. Okay, so that will give you the answer, 21816. So that is the required answer. Alright, yes. So this is just one of the ways of doing this question. We have already done this question by considering different cases. For this particular example, that method was easier, right? Because only very less number of cases, right? Only 3 or 4 cases. So we found all the cases, then added. Now here, this is the most general method. So here we have different values, but because the objects are not identical, distinct, so we have to use this selection also, right? Otherwise, we could have just found the number of solutions of this equation. Simply number of solutions of this equation. Because the objects are not identical, so we have to consider different cases. Alright, yes. So that's all. This is just one of the methods of doing the question. Okay. Consider 4 boxes where each box contains 3 red balls and 2 blue balls. If the blue balls are distinct and the red balls are identical in each box, in how many ways can 10 balls be chosen from these 4 boxes so that from each box at least 1 red ball and 1 blue ball are chosen? In this question we made a small change. Here the blue balls are distinct just like the last question, but the red balls are identical. Not all the red balls are identical. In one particular box the red balls are identical. They may be different from the other red balls in the other boxes, right? In one particular box the red balls are identical. Now with this condition we have to find the number of ways of selecting same 10 balls, right? Yes, almost the same idea, just make a small change in the method, you should be able to get the answer, right? So this question is for you to do, okay? The number of ways to place a knight and a bishop on a chessboard such that neither one can capture the other is. If you remember, we've already done a similar question based on the interaction between a knight and a rook, but this time we have a knight and a bishop. We almost have to use the same idea. We have to place these two pieces on the chessboard so that they are not in a position to capture each other, right? In how many ways can this be done? So the knight can move in an L shape like this, and the bishop moves in a line parallel to the diagonal, right? Either this diagonal or that diagonal. In how many ways can these two be placed on the chessboard so that they are not in a position to capture each other? See, first of all, we will count the total number of ways in which these two pieces can be placed without any restriction, total. From that, you subtract all the cases in which the knight can capture the bishop. And we also subtract the cases in which the bishop can capture the knight. So the remaining cases, so they will not capture each other, right? So let us count it. First, let us count the total number of cases in which the knight can capture the bishop. In how many ways can this be done? We will select a rectangle of size 2 by 3 like this. The rectangle is selected like this. Then if you place these two pieces on the two opposite corners, then the knight will capture the bishop. So that means, first of all, we have to select a rectangle of size like this. How many such rectangles are there in the entire chessboard? Let us count only in the first row. In the first row itself, how many such rectangles are there? Rectangles of size 2 by 3. How many are there? So 1, 2, 3, 4, 5, 6 rectangles are there. Similarly, we will calculate the number of rectangles in the first column. So how many? 1, 2, 3, 4, 5, 6, 7 rectangles are there. That means totally we have 6 multiplied by 7. 42 rectangles are there of size this 2 by 3. Okay, one such rectangle is selected. How many ways can this be done? 6 multiplied by 7, 42. Alright, yes. Now the number of ways the rectangle is selected, that is 6 in the first row. Similarly, first column 7. A rectangle is selected now. Now we have to place these two pieces. In how many ways can they be placed? See, first of all, let us place this knight. How many ways can this be done? See, there are 6 boxes, but we have to place this knight only on the corner, not at any other point. So let us select one of the 4 corners, right? That can be done in 4 ways, any one of the 4 corners. So the knight can be placed in any one of the 4 corners. So 4 ways it can be done. Okay, the knight is placed. But now we have to place the bishop. The bishop has only one choice. If a knight is placed in one corner, the bishop can be placed in the opposite corner only, right? Then only the knight will capture the bishop. So it has only one choice, the opposite corner. So that means this is multiplied by 1, that is the number of choices for the bishop. Okay, done. Now we have considered only the rectangle of size 2 by 3. It can also be a rectangle of size 3 by 2 like this, right? Vertical. So even here, if you place the two pieces on the opposite corners, still the knight will capture the bishop. So this is the number of arrangements for a rectangle of size 2 by 3. Same number of arrangements for the rectangle of size 3 by 2. So that means this is multiplied by 2. Okay, so this is the total number of ways we can place them so that the knight captures the bishop. If you do the calculation, 42 multiplied is, yes, so this is 336. Okay, so the knight captures the bishop in these many ways. Okay, done. Now we will consider the other case. The bishop captures the knight. The bishop will capture the knight when these two pieces are placed on a straight line parallel to the diagonal. Only then the bishop will capture the knight. Okay, but how many such lines are there parallel to that diagonal? Okay, let us consider this diagonal first. How many lines are there? So 1, 2, 3. So there are many lines. Okay, let us consider one by one because all these lines have a different number of boxes, right? So let us consider this lowermost one. Here only 2 boxes are there. So let us select 2 of them. Both of them we have to select. In how many ways can this be done? So that can be done in 2p2 ways. Okay, only 2. So 2p2 ways. Okay.
But for selection, the formula is only NCR.
It is not 2c2, it is 2p2, because we are not only selecting two squares, we are also arranging them. We are not arranging the squares, but we are arranging the two pieces in this row, right? That means 2 factorial ways we can arrange them. So first of all, we can select the squares in 2c2 ways, and arrangement can be done in 2 factorial ways. So that is what is written as 2p2, okay? Selection and arrangement. See, for example, consider the next line, which has 3 squares. We have to select 2 squares, right? So let us select them. So 3c2 ways we can select. After selecting the 2 squares, we have to arrange these 2 objects. So 2 factorial. So 3c2 multiplied by 2 factorial. So that we directly write as 3p2. So 3 boxes, we have to select 2 and arrange. So 3p2. Similarly, the next one, so that is 4p2. So like that. The next one is 5p2 plus 6p2, then 7p2. We are not considering the diagonal, so up to that point, like below the diagonal, so these many are there, but this should be multiplied by 2, because this is only the lower triangle, right, below the diagonal. Above the diagonal we have same number of arrangements, right, because 7, 6, so same number of rows. So this is only for the lower triangle. For the upper triangle, same number of arrangements. So what we do, this is multiplied by 2. Okay, so we have considered both the lower triangle and the upper triangle. Okay, done. Now we have to consider the diagonal also. The 2 pieces can be placed on the diagonal also, right? So how many squares are there in the diagonal? 8 squares, but we need to select 2. So that can be done in 8p2, right? Selection and arrangement. So 8p2. Okay, so that is the total number of ways we can place them. But we have considered only one of the diagonals, right? So this diagonal. It can also be the other diagonal, right? So same number of arrangements, other diagonal parallel to the other diagonal. We have these many lines. So multiply the whole thing by 2 again. So this whole thing is also multiplied by 2. Okay. That's all. The rest of the things just calculation. Alright, so let us do the calculation here. So 2p2, 3p2. We can calculate each value individually, right? Separately find the values and then add them, or we can follow some pattern here. So this is 2p2, 3p2. So we can use that summation, right? So that is sigma. So we can write it as, so 2p2, 3p2, etc. So that can be written as, so 2. So that is rp2, where r is from 2 to 7. Alright, so r is 2. So 2p2, 3p2 up to 7p2. So this thing is multiplied by 2 and then plus 8p2. That is separate. Okay, yes, that's all. So this value we have to find it. But what is rp2? rp2 is r multiplied by r minus 1, right? So that we can substitute here 2. This is sigma r multiplied by r minus 1. So that is 8p2. 8p2 value can be written. So r is from 2 to 7. So 8p2 value is what? 8 multiplied by 7. So that is 56. So multiplied by 2. So we have to find this. Okay, so that's all. So let us calculate this. What is this sigma r square, right? That is summation of all natural numbers, the squares of natural numbers, 1 square, 2 square, up to 7 square.
But r starts from 2, not 1.
It doesn't matter here. Even if you start the value of r from 1 to 7, so this value, the first term is anyway 0. If you substitute r1, this term is 0. So we can write it as r from 1 to 7. Still, the value will remain the same here because the first term is anyway 0. So this is summation 1 to 7 r square. And summation 1 to 7 r. That's all, right? Sum of squares of natural numbers up to 7, and similarly sum of natural numbers. So that is the formula. So we have the formula sum of squares. So that is n plus 1, 2n plus 1 divided by 6. So n is 7 here. So that is 7, 8, 15 divided by 6 minus the sum of all r, right? So that is n plus 1. So 7, 8 divided by 2. So plus 56 multiplied by 2. Okay, yes. Let's do the calculation here. So if you divide by 3, so it is 2, so this is 5, so that is 7 multiplied by 56 divided by 2, so that is 28. So here also we have 28, so 28 if you take out, so that will become 56 again. So 56 multiplied by, this is 5 minus 1 plus 56 multiplied by 2. So what is this value? So this is 4, 56 multiplied by 5 again multiplied by 2, so 56 times 10, so that is 560. So that's all. This is the total number of ways we can place these two pieces so that the bishop captures the knight. So here the number of ways in which the knight captures the bishop. Now we don't want these to happen, right? We have to place them so that they don't capture the other one. So that means, so this you have to subtract from the total. What is the total? We can place this knight in how many ways? 64 ways, no restriction. 64 ways because there are 64 squares, any one of the square. So 64 ways we can place, that is the total. 64. right? So this is our required answer. 64 ways totally we can place them, one of them, and then the other piece can be placed in 63 ways, right? Remaining, right? Any one of the remaining square, 60. This is the total. From this total, we have to subtract these things, okay? So that is minus 336 minus 560, right? So that's all. So if you do the calculation, we will be able to get the answer, right? So 64 multiplied by 63. So that is, okay, 4032 minus, this is 3, so 896, okay? So that's all. So this is 31, all right, 36. So that's all. So this is the total number of ways we can place these two pieces so that they don't capture the other, right? So that's all, right? So that is our required answer, okay? The number of ways to place three distinct rooks on a chessboard such that no one can capture the other is. This question is for you to do. We have three rooks here. We have to place them so that they don't capture each other, right? In how many ways can three rooks be placed so no one can capture the other, okay?
But two of the three rooks must be of same color. They don't attack each other.
No, assume that we have a modified chess game with three players or three different colors. That means any one of the rooks can capture any one of the other rooks, right? So that means three different players or three different colored rooks are placed, so no one can capture the other. So that is the condition. We have to place them so that they are not placed on the same line, because we know that the rook moves in a straight line parallel to the side. So two rooks come in the same straight line, so one can attack the other. So that should not happen. So we have to place them on different rows, right? Or different columns. So how many ways can this be done? Alright, this is very simple question, not like the previous one. In one line we can get the answer, right? So find the number of ways in which three rooks can be placed so that no one can attack the other. Alright, so think about it. A and B are subsets of a set containing 12 elements. Let X be the number of ordered pairs A, B. Which of the following options are correct? Here we are given a set containing 12 elements. A and B are given to be two subsets of the given set. We have to find the number of ordered pairs of subsets A and B satisfying certain conditions. The first condition is that n of A intersection B is 5. That means A and B have only 5 elements in common. How many ways can you construct these two sets A and B so that there are 5 elements common to A and B? Alright, so that is a very simple question. See the first question. So n of A intersection B equals 5. So that means these are the subsets, right? This is the bigger set and these are the subsets A and B. The intersection part, that means the common region, has only 5 elements. But which 5 elements? Any 5 from the 12 elements. So what do? Let us select 5 elements from the 12 elements and place these 5 elements in that region, right? Intersection part. So from the 12 elements of the set, you select 5 elements. And these 5 elements are placed in that common part. Done. No more elements should be placed in that region, right? The common region, A intersection B. Now, remaining we have 7 elements. 5 elements are already placed. Remaining we have 12 minus 5, 7 elements. These 7 elements can be placed in any one of the remaining regions. Which regions? Only A, right? The part of A, not including the intersection. Only A, and then only B, and outside A and B, right? These are the 3 regions where we can place the remaining 7 elements. So first element, for example, first element out of the 7 element can be placed in any one of the 3 regions. So it has 3 choices, here, here, or outside. So that means multiply this by 3 choices for the first element. Next element also has 3 choices, right? So again 3 regions, 3 choices. Next element 3 choices, 3 multiplied by 3, so 7 times. So 3 to the power 7. So this is the total number of ways we can place the remaining 7 elements, and these 5 elements are already placed in that region. Done. That's all. So this is the answer to the first question. So we can simplify this. 12C5 multiplied by, so 3 to the power 7. So it is 3 to the power 4. So 81 multiplied by 27. If you calculate that, there will be 2187. So that's all. So that is the answer to the first part, where the intersection has 5 elements. Okay, so that is done. Now let us consider the next case. Alright, so there n of A is less than n of B. That's all. So only this is the condition. N of A is less than n of B. Yes, now we have to consider combination of two subsets where the first set has less number of elements compared to the other set. Okay, yes, now what do? So this is done by A simple method. So what do you do? From the total number of possible combinations of A and B, total number of subsets, you subtract all the cases in which A and B have equal number of elements. You subtract the cases in which A and B have equal number of elements. If you subtract it, what are the remaining cases here? From the total, you subtract the cases in which A and B have equal number of elements. In the remaining cases, A is a bigger set or B is a bigger set. They have unequal number. Equal number we have removed. So that means in the remaining cases, A and B have unequal number of elements. That means either A is a bigger set or B is a bigger set. Alright. So in these many cases, either A is a bigger set or B is a bigger set. But we want B to be the bigger set. N of B is bigger than N of A. That means from the total, you make it half, right? Half of them, right? Out of the total, half of them will have A, bigger set, right? So A will be bigger set in half of the cases. In the remaining half, B will be the bigger set. So that means, so this you divide by 2. See, total minus equal. So that means unequal. So all the cases where A and B have unequal number of elements. Make it half because we don't want A to be the bigger set. We want B to be the bigger set, half of them. So half. That's all. Total. What is total? Totally how many ways the set A can be selected? So A is a subset. So how many subsets are there? 2 to the power n. That is the total number of subsets. Okay. B is also a subset without any condition, right? Total we are calculating. So that is 2 to the power n again. Minus A and B have equal number of elements. So how will you calculate that? So equal number. So if A has some 3 elements, B should also have 3 elements. So let us select 3 elements for A. Select 3 elements for B. That's all. If A has some 5 elements, B also should have 5 elements. So select 5 elements for this, select 5 elements for this. So NC 5 and here NC 5 again. So N is 12. So that means suppose A and B both have 0 elements. Okay, no elements. That means we can select that. So how many can you select? From the 12, you select 0 elements. No element is selected. And then for B also you select 0 elements. Okay, that is one possibility. Suppose A and B both have 1 element. That means 1 element should be selected for A, 1 element for B. So select them. So 12C1 multiplied by 12C1. And similarly, next 12C2, 2 elements, etc. like that. So last, suppose 12C12 multiplied by 12C12. All 12 elements are selected for A. So this thing divided by 2. Okay, so that's all. So that's it. So N is 12 actually, which means 2 to the power 24 minus, this is the formula, right? So NC0, NC0, NC1, NC1, NC0 square, NC1 square, NC3 square, sum of squares of binomial coefficients. So sum of squares of binomial coefficients. So that is formula 2NCN, right? So 2NCN is what? 2 multiplied by 12, 24C12. So the formula here is 2NCN, the sum of squares of binomial coefficients, right? Sum of squares. So 2, 24C12. So that thing divided by 12. So that's all. So this is our required answer. That's it. But you can simplify this further. So this we can write 2 to the power 24 minus this 24C12 can be written as 24 divided by 12. This is the property of the binomial coefficient, right? 24 divided by 12 multiplied by 1 less than that. That is 23C11. 24 by 12 is 2 divided by 2. So that can be divided. So if you simplify, we get 2 to the power 23 minus, this is 2 gets cancelled, so minus 23C11. So that's all. So this is the number of ways we can select the sets A and B so that N of A is less than N of B. Alright, if one set is less than the other, so we can do by this method. So that is the required answer. Okay. Now we have to consider the next case where we have two conditions. N of A intersection B is 5, just like this one, and also we have a condition N of A equals N of B, right? A and B have equal number of elements. So this is the first condition. So N of A intersection B is 5 and N of A equals N of B. Alright. So now this condition is similar to this one, right? So A intersection B has 5 elements. That means you select 5 elements and put them in the intersection part. So that means selection. So 12C5 selected. Now we cannot place the remaining 7 elements randomly in the other 3 regions like this. We have to place them in such a way that this part of A, that is A minus B, and that part of B, right, B minus A, these two parts have equal number of elements. In how many ways can this be done? Now we have to consider different cases. For example, this part has 0 elements, no element, and that part also should have 0 elements only. So that means from the 12 you select 0 elements, 12C0. Now 7C0, right, remaining 7, right, 5 elements are already placed, the remaining 7 elements you are selecting no element for this part, and that part should also have no elements. That means 7C0, 7C0 plus Next one. Now we have one element here, one element there, right? So one element, let us select one element. So that means 7C1 multiplied by, that part should also have one element only. In how many ways can this be selected?
Same 7C1?
No, this time it is not same 7C1 because this part and that part should have no common elements. A and B should have only 5 common elements which are already placed. Now this part and that part should have no common element. Once you select one element and place it in this part of A, now that same element cannot be placed in the other part, right? So that means from the remaining 6 elements, one element is already placed. From the remaining 6 elements, we have to select one element for that part, right? So that means it is 6C1 only. Alright, so not same 7C1, one element is already placed here, same element is not used again. So that means 6C1 only. Okay, this is the second case. The next case where we have two elements 7C2, right? Two elements are selected and placed it in this part of A. Now from the remaining 5 elements, right? So from the 7, 2 are already selected. So from the remaining 5 elements, you have to select 2 elements. Okay, done. Yes. Now the next case, 3 elements. Okay, so from the 7, you select 3 elements for this A, and from the remaining 4, you select 3 elements for the other one. Okay, so that's all, right? So that's all, right? No more, right? The next one will exceed this. So that's it. So this calculation will give you our required answer, right? So let us do the calculation. So that is 12C5 multiplied by, alright, so 7C0, 7C0, that is 1, plus 7 multiplied by 6, that is 42, plus 7C2, so that is 21 multiplied by 10, so that is 210, plus 7C3, so that is 7C3 is 35, 35 multiplied by 4, 70, 140. Okay.
Can't we add these terms using some binomial series instead of calculating each term separately?
Looks like some binomial series, right? 7C0, 7C1, 7C2, 7C3. But the other one is a problem. 7C0, 6C1, 5C2, it is not a constant, it's a variable. So 7, 6, 5, it's a variable. If that is also constant, we could have done it using some properties. Or if this is a variable, but this is a constant, suppose, that is also variable here, 0, 1, 2, 3. So both are variables, then it is difficult to do using binomial properties. We have to calculate each value separately. Okay, so that's what we have done here. So 1 plus 42 plus 210 plus 140. Alright, so this sum is 12C5 multiplied by, so this is 350, so 393. So that's all. So that is the answer. Alright, yes. So that's also, these are the different ways of selecting two subsets satisfying various conditions. Okay. Yeah. A and B are subsets of a set containing 12 elements. The number of ordered pairs A, B with n of A intersection B equal to 5 and n of A less than or equal to n of B is. This question is similar to the last question. We have the same condition, n of A intersection B equal to 5, but the other condition is a bit different, n of A less than or equal to n of B. So we have to consider all the cases that we did in the last question, combine them, we will be able to get the answer to this question, right? That is for you to try. Two people A and B are standing at two adjacent corners of a square grid of size 6 by 6. They move towards the diagonally opposite corners along the lines. They stop moving if they meet each other. The number of ways in which they meet at a point is. Here we have two people A and B standing at these two corners of the square. They start moving towards the opposite corners along these straight lines. That means from a particular point, the person A can move only in two possible directions. He can move in the rightward direction or upward direction, not in the opposite direction. If you move leftwards, that means he is going away from the opposite corner. He has to get to the opposite corner. That means he can move in the rightward direction or upward direction. Similarly, the person B can move in the leftward direction or upward direction. They start moving towards the opposite corners. But on the way, if they meet each other, the journey ends there. They don't proceed further. So we have to find the number of possible cases for that to happen. If at all they meet at a point, that point will be at an equal distance from these two corners because they are moving with the same speed. They will meet at a point which is at equal distance from these two corners, right? Where can that point be? That point can be any point on this straight line, right? So this is the middle line. If they meet at a point, that point will be on this straight line only. Let us name them, say P1, P2, P3 up to P7. These are the 7 points at which they can meet possibly, right? Now we have to consider different cases. Suppose they meet at the point P1. In how many ways that can be done? That means A has to get to the point P1 At the same time, B also has to get to that same point. Alright, in how many ways it can be done? Let us consider the general formula. Here we have a grid of size n by m. A person has to reach from one corner to the opposite corner. The number of steps taken by him is n plus m. Irrespective of the path he chooses, the total number of steps is always n plus m, out of which n are horizontal steps and m are vertical steps. The formula to find the number of ways to reach from one corner to the opposite corner is n plus m cn. Right? That is the formula you are supposed to remember. See, total number of steps is n plus m, out of which n are horizontal, so n plus m cn. Right? We can choose the number of horizontal steps, that is n plus m cn, or we can write it as n plus m cm. So that is the formula to find the number of ways to reach from one corner to the opposite corner. We can arrive at this formula using the combination of identical objects also. Simply you can remember this: total number of steps n plus m, out of which n are horizontal, so n plus m cn, that is the formula. Here also we have to reach the point P1 from this corner. So total number of steps is 3 steps. Out of these 3 steps, all the 3 steps are horizontal. Using the same formula, 3C3 is the number of ways for this person A to reach that point. 3C3, that's it. So 3C3 is the number of ways to reach the point P1 by that person A. Similarly, the person B also reaches the same point. That means he has to take the same number of steps, 3 steps. Out of these 3 steps, all the 3 steps are horizontal. That means again 3C3. So 3C3 multiplied by 3C3. So 3C3 squared is the total number of ways in which these two people meet at the point P1. Similarly, they can meet at the point P2 also. So let us calculate that. So for that, to reach the point P2, the total number of steps is 3 plus 1, 4 steps. Out of which 3 are horizontal. Out of 4 steps, 3 are horizontal. So the formula is 4C3. Similarly for the person B, right, 4C3. So 4C3 multiplied by 4C3. This is the total number of ways in which they meet at the point P2. But there is a problem here. This includes all the possible ways of reaching the point P2. One of the ways is through the point P1, right? But once they reach the point P1, they will not move to the point P2, right? Once they meet at one point, they will not proceed further. That means this includes that way also, reaching the point P2 through the point P1. But that should not be included because we've already included here meeting at the point P1. So here we should not include that, because when they pass through the point P1, they meet at the point P1, they will not move to the point P2. So that means we have to subtract the number of ways in which they first reach the point P1. So that is already calculated. So we have to subtract that. So from this we have to subtract that one, right? 3C3 square. Because once they reach the point P1, they will not move to P2. So we have to eliminate all the possible ways of reaching P2 through the point P1. So that is subtracted. This total is the number of ways of reaching P2 but not through the point P1. Alright, done. Similarly, when they meet at the point P3, so how many ways it can be done? So there are 5 steps totally, out of which 3 are horizontal. 5C3 square. Now again we have to subtract the cases in which they pass through the point P2, because once they reach the point P2, they will not move to P3. So that means we have to subtract this value, right? 4C3 square, because that is already calculated. So 4C3 square. This is the number of ways of reaching the point P3 but not through the point P2 or P1. Alright, yes, done. Now similarly the next point P4, P5, etc. So let us write directly the last one. Okay, so the last one, P7. So total number of steps is what? So 3 plus 6. So there are 9 steps. So 9C3 squared. That is the total number of ways they meet at the point P7. But we have to subtract the number of ways of reaching the point P6. So that is 8 steps and 3 are horizontal. So 8C3 squared. So now if you add this, we will get our required answer, right? Total number of ways. So meeting at the point P1, P2, P3, etc. So total is, if you add this 3C3 square, that gets cancelled, right? Minus here plus here, minus 4C3 square, etc. So if you cancel everything, we'll simply be left with the 9C3 square. So that's also, that is our required answer. If you do the calculation here, so 9 multiplied by, okay, 12 multiplied by 7. So that is 84. So 84 square. So that equals 7056. So that's all. This is the total number of ways in which these two people meet at some point, maybe at P1 or P2 or P3, etc. Right? 9C3 square. So that is the answer.
But 9C3 squared only takes into account the meeting point P7.
See, this 9c3 square not only includes the possibility of meeting at the point P7, it also includes meeting at the point P6, P5, etc. See, when you say 9c3 square, not 9c3 square minus 8c3 square. When you say 9c3 square, it includes all the ways of reaching the point P7, including the ways of reaching P7 through the point P6 or P5, P7. That means passing through the point P5, P7 is already included in 9c3 square. We could have written the answer directly also, not doing all this, but just to avoid confusion we have done one by one. So what is this 9c3 square minus 8c3 square? This is number of ways of reaching P7 but not passing through the point P6, because passing through the point P6 is already calculated here, right? That is not included. All the ways of reaching P7 is 9c3 square only, but we are subtracting this because we are eliminating all the cases in which first you reach P6 and then P7, because that is already calculated, right? So just to avoid confusion, otherwise we could have written the answer directly also. So we have calculated one by one, reaching the point P1, P2, P3, etc. If we add the total, so we get this answer 9c3 square. Is that okay? So that is our required answer, 9c3 square, the number of ways these two people meet at a point. Alright, 7056, that is the answer. Two people A and B are standing at two opposite corners of a square grid of size 6 by 6. They move towards the diagonally opposite corners along the lines. The number of ways in which they meet at a point is. This time A and B are at the opposite corners. They start moving towards each other. We have to find the number of ways for them to meet at a point. We have to use almost the same idea. I'll leave it to you. The number of positive integer solutions of the equation x, y, z equal to 5 to the power 6 multiplied by 3 to the power 9 with HCF of x and z equal to 1 is. Here we have to find the number of combinations of three numbers whose product is 5 to the power 6 multiplied by 3 to the power 9. We have a standard method of calculating the number of solutions when the product is given. But here, in addition to that, we also have a condition, the HCF, the highest common factor of x and z is 1. That means x and z have no common factor except 1. With this additional condition, we have to find the number of solutions of this equation. Alright, yes. Now for when the product is given, we have to find the number of solutions using this method. See, x, y, z, this product is given. That means x is a factor of that number. X, y, z is that number, 5 to the power 6 multiplied by 3 to the power 9. That means x is a factor of 5 to the power 6 multiplied by 3 to the power 9. Y is a factor and so is z. So that means any number which is a factor of the given number is of the form. See, x, y, z is given to be that number. That means x is a factor which can be written in the form. So 5 to the power something, right? So we take it as x1. And similarly 3 to the power something, that is taken as x2, right? Because the only prime factors are 5 and 3. So this number x must be of the form 5 to the power x1, 3 to the power x2. x1 can take values from 0, 1, 2, 3 up to 6 maximum. Similarly x2 can take values up to 9, right? Similarly y is a factor of this number. So y can also be written as 5 to the power some value, take it as y1, and 3 to the power y2. So z is a factor of the same number, so z can also be written as 5 to the power z1, 3 to the power z2. Okay, now if you multiply these three numbers, we should get that number, right? 5 to the power 6. So if you multiply these numbers get added, right? So that means x1 plus y1 plus z1, the total power, that must be equal to 6, right? Similarly, if you add these variables, right, x2, y2 and z2, we should get x2 plus y2 plus z2. So this sum is equal to 9, right? That is the total power given. Now we have to write the number of solutions of this equation. Now it is addition. So we have a direct formula to write the number of solutions of this equation and also this equation. But this x1 and z1 have some restrictions, right? See, if there are no restrictions, what is the number of solutions? We have the formula n plus r minus 1 c r minus 1. That is the number of solutions of an equation of this type. Here three variables and n is 6. That means 6 plus 3 minus 1 c 3 minus 1. That is the total number of solutions of this equation, right? Non-negative integral solution. But these two numbers x and z should not have a common factor except 1. That means what? This x1 and z1 should not be non-zero at the same time. See, if x1 and z1 both are more than 0, right? Suppose x1 is 1 and z1 is also 1. That means 5 is a common factor, like 5 to the power 1, 5 to the power 1. So x and z have a common factor 5. Even if this value is more than 1, if it is 5 square, still it has a factor 5, and this is 5 to the power more than 1, right? So that is 2, 5 square. So this is 5 to the power 3. So whatever it is, if this number, one of these numbers is not 0, so these two will have a common factor. So our condition is that either x1 or z1 must be 0. Okay, one of them should be 0, right? Otherwise, so these two numbers will have a common factor. What do we do? First, we will write all the solution, total number of solutions without any restriction. So here 6. So that means 6 plus 3 minus 1 c 3 minus 1. That is the total number of solutions, right? N plus r minus 1 c r minus 1. That is written. From that you subtract the cases in which x1 and z1 are non-zero. We want one of them to be 0 at least, but you subtract the cases in which neither one is 0, right? So this is minimum, say 1, and z1 is also minimum 1. So you remove all the cases. In the remaining cases, one of them must be 0. So what do you do? Subtract. This is minimum 1, alright? So that means 1. So z1 is also minimum 1, alright? So we assign 1 to these numbers. That means this is not 6 now. So 1 assigned already. So that means this is 4. So this is our new equation, x1 plus y1 plus z1 equal to 4. So how many solutions are there? So same formula, 4 plus 3 minus 1 c3 minus 1. So this is the number of solutions with this condition that x1 and z1 are non-zero. Okay, we subtract from the total, we get the number of solutions in which one of them is 0. Okay, yes, now that is done.
But x1 and z1 have fixed values 1, the only variable is y1.
See, this is not the exact value of x1, it is only the minimum value of x1. Similarly, 1 is the minimum value of z1. We assign minimum value 1 here, 1 here. Then this becomes 4 now. From the total 6, we assign 1 here, 1 here. This becomes 4. Then this 4 is distributed over all these 3 numbers. Which means if you put one more number here, it will become 2. And if you put one more here, it will become 2. So this is only the minimum value, right? So minimum value is 1. If you put any more number here, so that will become more than 1. So in any case, even if you assign 0 here, so then this will become 1 plus 0, 1. So 1 is the minimum value of x1. So 1 is the minimum value of z1, right? So that means the remaining 4 is distributed over all these 3 numbers. Alright, so that means our new equation is now x1 plus y1 plus z1 equal to 4. So that has solution, this one, 4 plus 3 minus 1 c 3 minus 1. Is that okay? Now the same thing is to be done for this equation also. Let us write the total number of solutions. So here 3 variables, 9 is the value of n. So that means 9 plus 3 minus 1 c 3 minus 1. That is the total number of solutions. From this you subtract the cases in which these two numbers are not equal to 0, which means minimum 1. So that means this will become 7, right? From 9, so this minimum value x2 is minimum 1. 1 is assigned to this, 1 is assigned to z2 also. That means the total is 7 now. So what is the number of solutions now? So minus 7 plus 3 minus 1 c 3 minus 1. Okay, so that's all. Just do the calculation, we will get the answer. So this is 8c2 minus this is 6c2 multiplied by, so that is 11c2 minus 9c2. So let us do the calculation here. So 8c2 is 28 minus 15 and 11c2 55 minus 36. Okay, so 28 minus 15, that is 13 multiplied by, this is 19. 13 multiplied by 19, so that is 260 minus 13. So that is 247. So that's all. This is the number of solutions of this equation satisfying that given condition that x and z have no common factor except 1. See, what we did is simply this. We found the total solution, subtract the solutions in which both these values are non-zero. One of them must be 0, right? Either x1 or z1 must be 0, at least one of them. So you remove the cases in which both of them are non-zero, and here also we did the same thing. Alright, so the number of solutions of this equation x, y, z equal to the given number, right? The product is given with the additional condition. So we have the number of solutions, this one, 247. Okay. The number of positive integer solutions of the equation x, y, z equal to 5 to the power 6 multiplied by 3 to the power 9 with HCF of x, y and z not equal to 1 is. Same question, but the condition is a bit different here. The product of three numbers is given. We have to find the number of solutions with the condition that the HCF of these three numbers is not equal to 1. That means these three numbers have a common factor apart from 1, right? Apart from 1, there is one number that divides all these three numbers. With this condition, we have to find the number of solutions of this equation.
Like the last question, can we subtract all the cases in which the numbers have a common factor?
No, we don't need to subtract anything. We can do this question directly. If you try to subtract the cases in which the HCF is equal to 1, there will be a lot of confusion. See, when two numbers have a common factor, they don't have a common factor with the third one. Then also the HCF is not equal to 1. So we have to subtract all these cases, right? We cannot simply subtract the cases in which these three numbers do not have a common factor. Maybe two numbers have a common factor and no common factor with the third one. So there are a lot of cases to be considered. So we don't need to subtract the cases. We can do this directly. So this is a very simple question. So that is for you to try. The number of three-digit numbers with sum of digits less than or equal to 20 is. Here we have to find the number of three-digit numbers, sum of whose digits is less than or equal to 20. We have a three-digit number. That means it is a combination of three single-digit numbers. If you add these digits, we will get a value which is less than or equal to 20. We have to find the number of possible combinations. Let us take these three digits to be x, y and z. If you add them, we get a number which is less than or equal to 20. See, this is the condition. If you add these three digits x plus y plus z, that is less than or equal to 20. We have to find the number of solutions. But this is an inequality. We can convert this into an equation. So this value is less than or equal to 20. So that means with this value, if you add something, that will be equal to 20. Whatever this value is, suppose this is 15. If you add 5, it will be equal to 20. Whatever this value is, if you add something, it will be equal to 20. So that added value, so that is taken as k. So that equals 20. Now it is a question of four variables like x1 plus x2 plus x3 plus x4 equal to n. What is the number of solutions? We have the formula n plus r minus 1 c r minus 1. Yes. Now, but we have a restriction here. We can't randomly select values for this x, y and z because they are single digit numbers. Maximum value x can take is 9. Similarly, y can be maximum 9, right? It cannot exceed 9. When there is upper limit, we have a problem. When there is lower limit, we can directly do this question, assign minimum value to each variable and then we can find the number of solutions. But when there is upper limit, we have to do a lot of calculations. See, x, write the possible values of x as the powers of x, right? We are going to use that coefficient multinomial method. See, write the values of x. What are the possible values of x? Write it as powers of x. From that, you write the coefficient of x to the power 20. The total is 20. You find the coefficient of x to the power 20 in this expression. Coefficient of x to the power 20 in the expression. What are the possible values x can take? 1, 2, 3 up to 9. It cannot take value 0 because the first digit cannot be 0, right? Minimum value is 1 and maximum value is 9. So the powers of x can be x to the power 1 and x square, etc. up to x to the power 9. So 9 is the maximum value. Similarly, for the variable y, we have the restriction. It can be 0, right? Because the second digit can be 0. 0, 1, 2, 3 up to 9. These are the possible values of y. So you write it as powers of x again. So that is x to the power 0. It starts from 0. And x to the power 1, x square up to x to the power 9. Similarly, for the variable z takes the same values, right? 0, 1, 2, 3, etc. So that means we have to write the same expression again, or you write it as a square, right? This is for y and z. And for the variable k, so what are the values k can take? So that is x to the power 0, x to the power 1, x square, etc. It can go up to infinity. Okay.
But k can only take values till 20, not infinity.
Yes, the maximum value of k is 20 because the total itself is 20. K cannot exceed 20 obviously, but we are not imposing that condition. That happens automatically. We have taken this value up to infinity, but still you will get the same answer because we are only finding coefficient of x to the power 20. If you stop here up to x to the power 20, or if you include few more terms x to the power 21, 22, 23, the answer will not change because any higher power of x, right, x to the power 21, 22, etc., they will not contribute to our answer because when you say x to the power 20, the higher powers can be ignored, or even if you include them, the answer will be same, right? But here we are imposing restriction. right? This restriction is given in the question, but this restriction that happens automatically. We can take up to infinity, you will get the same answer. Okay, yes. Now we have to find the coefficient of x to the power 20 in this product. Okay, let us simplify this. So this is a geometric progression, so we have to find the sum of GP. So sum of GP, so what is that? X multiplied by 1 minus x to the power 9 divided by 1 minus x. So this is also a GP. So first term is 1, so that is 10 terms are there. 1 minus x to the power 10 divided by 1 minus x squared. That is sum of infinite GP. So that is 1 minus a divided by 1 minus r. So that is 1 divided by 1 minus x. Okay, yes. So now we have to multiply. So this is, you divide by this x, right? So we have to find the coefficient of x to the power 20 in this. Now if you divide by x here, so this will become 19 because already x is there. We only need coefficient of x to the power 19 from this expression. So that means, so coefficient of x to the power 19 in this expression. So dividing by x, you will get 1 minus x to the power 9 and multiplied by, so this is a plus b squared, right? So we can use the formula 1 minus 2ab. So that means 2x to the power 10, and the next term is x to the power 20, right? X to the power 20. We don't need to consider that because we only need the maximum power x to the power 19. Any higher power, right? 20 will not contribute to our answer, so we can stop it here. We are not writing the next term. So 1 minus x squared and 1 minus x. So if you multiply all this, you will get 1 minus x to the power minus 4. So from this we have to find the coefficient of x to the power 20. But there are many terms, right? We have to multiply this first. So this is 1 minus x to the power 9 minus 2x to the power 10 plus 2x to the power 19 multiplied by 1 minus x to the power minus 4. Okay, yes. Now this term, each term should be multiplied with that expression, and then we have to find the coefficient of x to the power 19. So 1 multiplied by the coefficient of x to the power 19 from this. So that is a formula. You're supposed to know this formula, 1 minus x to the power minus r. An expression like this, we want the coefficient of x to the power 9. So this is the formula. From this one, 1 minus x to the power minus r, we want the coefficient of x to the power 9, x to the power n. So that as formula n plus r minus 1 c r minus 1. This is the formula we generally use it directly without using this method. But here we have to use this method. So this is the formula that you have to remember. The coefficient of x to the power n in 1 minus x to the power minus r is n plus r minus 1 c r minus 1. We want x to the power 19 in this 1 minus x to the power 4. So that as formula 19 plus 4 minus 1 c 4 minus 1. Alright, n plus r minus 1 c r minus 1. Now the next term minus, now x to the power 9 multiplied by this term. So when you have x to the power 9 already, we want x to the power 19. From this we only need x to the power 10 because x to the power 9 is already there. We only need x to the power 10. So that multiplied by this will give you total x to the power 19. So that means this multiplied by coefficient of x to the power 10 only. So what is coefficient of x to the power 10? So that is the same formula again. It is 10 plus 4 minus 1 c 4 minus 1 and then minus 2. X to the power 10 is there already. X to the power 10 multiplied by, we only need x to the power 9 term, right? So coefficient of x to the power 9, 2 multiplied by x to the power 9. So x to the power 9 coefficient is, so 9 plus 4 minus 1 c 4 minus 1. Okay, yes. Now the last term, 2x to the power 19. So we only need x to the power 19, which means we need the constant term from this. What is constant term? So that is the first term, right? 1. So 1, that's all. So that is the value. So 2 multiplied by 1. So that is the coefficient of x to the power 19 from all these terms. Alright, if you simplify this, so this is 22 c3 minus 13 c3 minus 2 times 9 plus 3. So 12 c3 plus 2. Okay, so that's all. So this is the required the value, right? So the number of solutions of this equation. So what did we do here? First of all, this is an inequality. We convert this into an equation. So that gives you a 4 variable question. Okay, now we have restrictions here. If there are no restrictions, we need not have done all this. We could have directly written the formula n plus r minus 1 c r minus 1. Because there are there are restrictions, like the upper limit is given, we have to use this coefficient method, right? Because each variable has some limit, right? There is an upper limit, so use these powers are the possible values of these variables. In this product we have to find the coefficient of x to the power 20, and finally we get this answer. Alright, so that is the answer to the question.
I remember doing similar question using inclusion-exclusion principle.
We can use inclusion exclusion method. It's a bit tricky, but we will try that also. We have this equation x plus y plus z plus k equals 20. Alright, so we have to write the total number of solutions satisfying our condition. First of all, we will write all the solutions without any restrictions. Obviously x cannot be 0, right? The minimum value of x is 1, so that we have to consider anyway. So the minimum value of x is 1, that means 1 is already assigned here, minimum value, not the exact value. That means this total will become 19 now, not 20. So what is the total number of solutions? So that has the direct formula. So 19 plus 4 minus 1, see 4 minus 1. This is the total number of solutions without considering the upper limit. Okay, now we have to subtract the cases which do not satisfy our condition. For example, the first number exceeds 9. So first number is minimum 10, suppose. The first number is minimum 10. That means it does not satisfy our condition. We are going to remove that. If the first number is minimum 10, that means the total will become, instead of 20, it will become just 10. Okay? Because 10, 20 minus 10. So that is 10. So this 10 is the total x plus y plus z plus k is 10 now. So what is the number of solutions? So same formula. So that is 10 plus 4 minus 1, see 4 minus 1. So this is the number of solutions where the first number x is more than 9. Okay. Similarly, what if the second number is more than 9? So y is more than 10, more than 9. So that means y is minimum 10. That is the next case. So y is minimum 10. Y is minimum 10. So same condition. So this will become 10 again, because minimum value of y is 10, that is assigned here. That means the new variable equation is x plus y plus z plus k equal to 10. How many solutions? So that is the formula. But remember, when y is minimum 10, already x is minimum 1. So x is minimum 1, right? Because x cannot be 0. That means it is not even 10. This is 9 only, because 10 plus 1, 11 already assigned. So remaining 20 minus 11, that is 9 only. So what is the total number of solutions? That is 9. So we have to subtract. So this is 9 plus 4 minus 1, see 4 minus 1. So this is the number of solutions in which the second variable y exceeds 9. Okay, these many solutions. Okay, similarly, in how many ways we can find solution with z more than 9? So that will be same thing, right? Same as y, right? Y and z have no difference, right? The same value, right? Same concept. So y exceeds 9. These many solutions. Similarly, if z exceeds 9, so same number of solutions. What do you do? Instead of writing this again, we just multiply this by 2. Okay, so that is done. Now we have to add all the cases in which we have subtract the cases in which one of the number exceeds 9. Okay, one of the number, either x or y or z. Now we have to consider the cases in which two numbers exceed 10, right? What if two numbers are minimum 10? Suppose x is 10 and y is also minimum 10. That means what is the total now? 20 minus 20, so that is 0. So 0, right? That means x plus y plus z plus k is equal to 0. How many solutions are there? Only one solution, right? All 0. 0 plus 0 plus 0. See, this is minimum 10. So 10 plus 0, so that is 10. So 10 plus 10 plus 0 plus 0 equal to 0. That is the only solution. So that means 1. We have to add 1. Alright. Now the next case where the first number x and the third variable z that exceeds 10, right? Minimum 10. So then also we have this 0, right? Total is 0 because 20 minus 20 0. How many solutions? Again same number of solutions, right? 10 plus 0 plus 10 plus 0, that is the only solution. So one solution. And we have to consider the next case where y and z exceed 9. Is it possible? Why? If y is minimum 10, z is also minimum 10, so already 20, but x has to be minimum 1. That means 10 plus 10 plus 1, 21. But total itself is 20, so that is not possible. So either x and y can exceed 9 or x and z can exceed 9, but y and z can never exceed 9, right? So these are the only two cases. That's all. So let us simplify this. So this is 22 C3 minus, so this is 13 C3 minus 2 times, that is 9 plus 3, that is 12 C3 plus 2. So that's also, that is the required answer, right? So we can use inclusion exclusion principle also to solve this question, right? So when there is upper limit for equations of this type, we can use this method also, right? So the first method is using the variable, right, the coefficient method, right? Write the values of x, the values of the variables as the powers of a variable, and then find the coefficient of the total x to the power 20. So that is the usual method we do. We can also use this inclusion exclusion method to get this answer. Okay, yes. The number of 3-digit numbers greater than 300 with sum of digits less than equal to 15 and greater than equal to 9 is. Okay, same type of question. Here also we have 3-digit numbers, sum of whose digits is not only less than equal to 15 but also greater than equal to some number 9. With these two conditions, we have to find the number of 3-digit numbers, right? So that is for you to do. The number of ways to put 11 distinct balls in 4 distinct boxes such that the first 3 boxes contain odd number of balls is. Here we have 11 balls. We have to place these 11 balls in these 4 boxes with the condition that the first 3 boxes should contain only odd number of balls. If this condition was not there, we could have written the answer directly. The first ball can be placed in any one of the 4 boxes, so 4 possibilities. Second ball can be placed in 4 ways. Third ball can be placed in 4 ways again. So totally 4 multiplied by 4 multiplied by 4 etc. 4 to the power 11. That would be the answer if this condition was not there. Now we have a restriction. The first 3 boxes should contain only odd number of balls. With this restriction, we will find the number of ways to put these balls in the boxes, right? Suppose we place x number of balls or x1 number of balls in the first box. And the second box contains say x2. Third box x3, fourth box x4, but x1, x2, x3 all are odd numbers, right? Now we have to find the number of solutions. See, the first box contains x1 balls, second box x2, and third x3, and then x4. But this total must be equal to the total number of balls, that is 11. But remember, the number of solutions of this will not give you the answer because the balls are not identical. The balls are distinct. If the balls are identical, the number of solutions of this will give you the answer. Of course, these 3 numbers should be odd numbers, but here the balls are not identical. That means not only the number, also which ball goes into which box, that also matters here. See, let us use this method, right, the coefficient method. So the total here is 11. That means we have to find the coefficient of x to the power 11. Coefficient of x to the power 11 in this expression. What are the possible values of x1? So x1 should be an odd number. That means it can be, write the possible values of x1 as powers of x. So x to the power 1. Next x cube, no x square because only odd numbers. Similarly x to the power 5 etc. Alright, similarly x2 can also take only odd numbers. That means same expression again. So that means we can write it as a square. x3 also has the same restriction. That means cube. Okay, so from this we have to find the coefficient of x to the power 11. Also we have this variable x4. So that can take any value. So no problem with that. So that is 1 plus x square etc. Alright, yes, from this we have to find the coefficient of x to the power 11. Okay.
But x4 can only take even values as the sum is an odd number.
See, again, just like the other question, we are not imposing that condition. That happens automatically. See, when the first 3 numbers are odd numbers, this number will be an even number because the total is an odd number, right? We don't need to apply that condition because anyway that number is an even number. If you consider only even powers, you will still get the same answer, right? Because that condition is automatically satisfied. So, but to make it easier, I consider this series. If you consider only x square, x to the power 4, etc., you will get the same answer, right? Yes. Now, we have to find the coefficient of x to the power 11 in this expression. That will not give you our answer, right? Because this is only when the balls are identical. Right, here only we are counting the numbers, how many balls here, how many balls here, etc. But which ball also matters here, right, because these balls are distinct. So what we have to do is, once you fix the numbers, how many number of balls in the first box, second box, etc., we can also arrange these balls, right? Because which ball goes into which box, that also matters. We have to arrange them also. But how many balls are there totally? 11 balls. We can arrange them in 11 factorial ways. So this should be multiplied by 11 factorial ways. Right, so multiply this by 11 factorial. All right, yes, But there is a problem because once the balls are placed inside the box, there is no arrangement, right? Inside the box, we don't know which one is the first ball, second ball, no arrangement, right? So that means when the balls are inside the box, no arrangement. But totally we have to arrange them, right? Yes. Now how many ways can you arrange them? 11 factorial. But what is the meaning of this x cube x to the power 5? This x cube means the first box contains 3 balls. When 3 balls are inside the box, we are not going to arrange them. So we have to divide this by 3 factorial. Right? So we have to divide by 3 factorial. Just like identical balls, inside the box, they are like identical balls because they are not going to be anyway arranged. Overall, there is arrangement, but inside the box, no arrangement, divide by 3 factorial. Now we have 5 balls, no arrangement, so divide by 5 factorial. So here, 1 ball, 1 factorial anyway. So that means, so there also we have 1 x by 1 factorial, x squared by 2 factorial, etc. Right? So now arrangement, this 11 factorial and these values will not be there if these balls are identical. Because they are distinct balls, we have to arrange them 11 factorial, but inside the boxes there is no arrangement, so divide by that factorial. Alright, yes. So now we have to find the coefficient of x to the power 11 in this expression. So how will you find that? So this is the exponential series, right? This is exponential series. So we have to find the value of the exponential series and then multiply. From that you find the coefficient of x to the power 11, right? So what is this exponential series? So that is e to the power x, right? 1 plus x by 1 factorial, x squared by 2 factorial, etc. But here only odd powers are there. So what is the exponential series which contains only odd powers? So that has this formula, 11 factorial multiplied by, so this is the exponential series of only odd power, e to the power x minus e to the power minus x divided by 2, okay, the whole cube. So that is simple exponential series e to the power x, that's all, right? So this is only for odd powers, okay. Let us simplify this. So this is 11 factorial divided by 2 cube is 8, so we use a minus b whole cube, right, formula. So that is e to the power 3x minus 3 e to the power x plus 3e minus x minus e to the power minus 3x multiplied by e to the power x, right? So let's simplify this further. So 11 factorial divided by 8, if you multiply that, so it will become e to the power 4x minus 3e to the 2x plus just 3 minus e to the power minus 2x. Let us write the coefficient of x to the power 11 in this expression, that's all. So this is constant anyway, 11 factorial divided by 8 multiplied by, what is the coefficient of x to the power 11 in this? So that is 4 to the power 11, right? Because, so what are the terms of this e to the power 4x? 1 plus 4x by 1 factorial, 4x squared divided by 2 factorial, and then 4x to the power 11 divided by 11 factorial. So the coefficient is 4 to the power 11 divided by 11 factorial. So that is, okay, minus similarly e to the power 2x, what is the coefficient of x to the power 11? So that is 2 to the power 11 divided by 11 factorial. So plus, so this 3 will not give you any coefficient, so minus, this is minus 2 to the power 11 divided by 11 factorial. So that's all. So let's simplify this. This 11 factorial gets cancelled here, and then this is minus 3 times 2 to the power 11, this is plus 2 to the power 11, right? So minus of minus, that is plus 2 to the power 11. So that is, so this is 1 by 8, 4 to the power 11 minus 2 times 2 to the power 11. So that is, okay, 2 times 2 to the power 11. Okay, so that's all. If you simplify this, this is 2 to the power 22, right? 2 to the power 22 divided by 2 to the power 3. So that equals 2 to the power 19 minus, this is, if you cancel this 2, so this is 2 to the power, okay, so 9, that's it. Okay, so that's all. This is the total number of ways we can place these balls in the boxes with this restriction, right? So we have to deal with this question in a different way if the balls are identical or if there are no restrictions, right? But here there is a restriction and also the balls are distinct, so we have to do by this method. All right, yes. So this 11 factorial and these factorials are because the balls are distinct. If these balls are not distinct, so these things will not be there. All right, yes. So that is the answer to the question. The number of ways to wear 11 distinct rings on 4 fingers such that the first 2 fingers have odd number of rings. Here we have 11 rings. We have to put these 11 rings in 4 fingers. How many ways can this be done?
Isn't this same as balls in boxes?
No, there is a difference between balls inside a box and rings on a finger, because when the balls are placed inside a box, there are no arrangements. Inside a box, there are no arrangements. But when you consider rings on a finger, we have to consider arrangements also, because which ring is first, which ring is second, that makes a difference. So that makes this question even easier. We don't need to consider any exponential series, simple series, right? We can find the answer directly. It is easier than the last question. That is for you to do. The number of ways to select 4 numbers x1, x2, x3 and x4 from the set 1, 2, 3 up to 20 with x1 less than x2 less than x4 such that the sequence xi plus 1 minus xi is an arithmetic progression is. Here we have the set of first 20 natural numbers. From this set we are selecting 4 numbers x1, x2, x3 and x4 which satisfy certain conditions. The difference between the consecutive terms x2 minus x1, x3 minus x2 and x4 minus x3, this forms an arithmetic progression. With this condition we have to select 4 numbers, right? So for example, let us select the first number x1, here 2. So 2 is x1 and next number is say 4 and next number is 7 and next number is 11. So the difference between the terms, right, 4 minus 2, 2 and then 7 minus 4, 3. So this 2, 3 and 4, these are the differences between the consecutive terms. They form an arithmetic progression. This is one such example. We have to select 4 numbers satisfying this condition, right? Yes. What we do, let us select the first number, say 2. That means before selecting the first number, we have left some elements right here. So that is taken as y1. So y1 is the number of elements not selected before selecting the first element. So y1 value is 1 here. Similarly, the next gap, right, after selecting the first number x1, before selecting the second number x2, we have left some gap. That gap is taken as y2. So what is the value of y2 here? That is 2, right? 1. And similarly, the next gap, right? So between this x2 and x3, that gap is taken as y2 plus d, because these differences should form an arithmetic progression. So this gap is y2, so the next gap will be y2 plus d. Similarly, the next gap is y2 plus 2d, because these numbers should form an arithmetic progression. And the last set of numbers not selected, that is taken as y3. Alright, so these gaps add up to the totally 20 numbers, out of which 4 are already selected. So these numbers are not selected. So this total must be equal to 20 minus 4, that is 16, right? Yes. This is our equation. First number y1, right? y1 is the first number not selected. And then next gap, that is y2. And then y2 plus d. Then y2 plus 2d. Plus y3. So this total must be equal to 16, because these are the numbers not selected. Totally 4 numbers are selected out of the total of 20. So 20 minus 4, 16, right? So let us simplify this. This is y1 plus y3 plus y2. So 3 times y2, right? Similarly, 2 plus 2d. So that is 3d. So 3 is taken out, so plus 16. Alright, so that's all. We have to find the number of solutions of this equation. That's it. But this is not a simple equation, because there is a 3 here. If this 3 was not there, we could have directly written the solution using the formula n plus r minus 1 c r minus 1. But this 3 is there, so we have to consider many cases. What are the possible values of this y2 plus d? So let us write all the possible values. Starting with the simple one, that is y2 plus d equal to 0. That is the smallest possible value. What if this y2 plus d is 0? This equation will become y1 plus y3 equals 16, right? So that implies y1 plus y3 equals 16. So let us write the number of solutions here. y2 plus d equals 0. That means how many solutions are there? Only one solution, right? So here 0 plus 0 equal to 0. Is there any other possibility? So only one solution, 0 plus 0, that's all. So that means the number of solutions here is just 1. So we are writing the number of solutions of this equation. Similarly, let us write the number of solutions of this equation. So this is the same formula, n plus r minus 1 c r minus 1. So 16 plus 2 minus 1 c 2 minus 1. That is 17c1. 17c1 is just 17. So 1 multiplied by 17, that is the total number of solutions of these two equations together. Alright, done. Now the next case.
But y2 and d can't be 0. If the common difference is 0, The terms are equal.
No, even if y2 is 0, still the numbers are not equal. See, y2 is 0. What does it mean? The difference between the terms will be 1, not 0. See, y2 is not the difference between the terms. See, for example, here the number 2 is selected and the next number is 4. So x1 is 2, x2 is 4. So what is the difference? The difference is 4 minus 2, 2. But what is the value of y2? That is 1. So 1, that is not the difference between the two terms. The difference between the two terms is 1 more than the value y2. So that means if y2 is 0, that means the difference is 1. So even if you take the least value 0, still the common difference is not 0. Alright, so y2 can be 0. Alright, still the common difference is not equal to 0, that is minimum 1. Alright, so these values can be 0. Okay, now let us take the next case. y2 plus d is 1. Alright, y2 plus d equals 1. In that case, we will get y1 plus y3, 16 minus 3, that is 13. So let us write the number of solutions. y2 plus d equals 1. How many solutions are there? Same formula, 1 plus 2 minus 1 c 2 minus 1. So that is just 2, right? Number of solutions 2. Similarly here, y1 plus y3 is 13. That means 13 plus 2 minus 1 c 2 minus 1. So that is simply 14. See, we can directly write the answer here when only two variables are there. We have only two variables, then the number of solutions is just one more than this, 13. So we have 14 solutions. Alright, so here also 1, that means 2 solutions. Let us write the next case. So y2 plus d equals 2. That means this becomes 6. So y1 plus y3 is 16 minus 6. So that is 10. So y1 plus y3 equals 10. So let us write the number of solutions, that is 2. So that means 3 multiplied by, so 10. So 11 solutions. So like that we can keep writing all the cases. Let us directly write the last case. So what is the maximum possible value of y2 plus d? That is 5. If this is 5, 3 times 5, 15. It cannot exceed 5. If it is 6, 3 times 6, that is 18. The total only is 16. So that means the last value. So directly write. So y2 plus d equals, say, 5. If this value is 5, so 3 times 5, 15. So y1 plus y3, so that becomes equal to 1. So how many solutions are there here? So this becomes, so 5. That means 6 solutions. Multiplied by, so this is 1, that means 2. So we have to add all this. Okay, the total number of solutions. So we have to add all this. We need not find all these values because these numbers form a pattern, right? 1, 2, 3, 4, that means simple natural numbers. 17, 14, 11. So they form an arithmetic progression. What we do, let us write the general term and use the summation. See, this series, these numbers, so first number is 1, 2, 3, 4. So R, the term is just R. And this is an arithmetic progression, right? 17, 14, 11, etc. So 6 terms are there. What is general term of this arithmetic progression? The common difference is minus 3. So that means we can write it as, so 17. So 20 minus 3R. So that is the general term. We have to find the summation now. See, the first term is 20 multiplied by summation R. That is sum of all natural numbers up to 6, right? So sum of all natural numbers, n plus 1 divided by 2. So here it is 20 multiplied by, so n plus 1. So 6 multiplied by 7 divided by 2 minus, so the next term, so that is 3 times R squared. So 3 multiplied by that sigma R squared, right? What is sum of all squares of natural numbers? So n plus 1, 2n plus 1 divided by 6. So here it is 6 multiplied by 7, 13 divided by 6. So if you simplify this, so if you take out say 7, so we get so 10 multiplied by 6, so that is 60 minus, so that is 3 multiplied by 13, so that is 39. So we get 21 multiplied by 7. So 21 multiplied by 7, that is 147. So that's all. So this is the answer, right? This is the number of ways in which we can select 4 numbers, x1, x2, x3 and x4, satisfying this condition. The difference between the consecutive terms form an arithmetic progression. Alright, so that is the answer. The number of ways to select 3 numbers x1, x2 and x3 from the set 1, 2, 3 up to 20 such that xi plus 1 minus xi is greater than or equal to I plus 3 is. Here also we have to select some numbers from the set of 20 natural numbers. Only 3 numbers here, x1, x2 and x3, satisfying certain condition. The difference between the consecutive terms here should be greater than or equal to I plus 1. xi plus 1 minus xi is greater than or equal to I plus 1. That means x2 minus x1 is greater than or equal to 1 plus 3, that is 4, right? Similarly the other one. So with this condition we have to find the number of ways to select these 3 numbers. This question is very simple. We need not consider different cases, right? Simply almost we have to use the same idea. We have to take the gaps to be some variables, right? y1, y2, etc. But this lower limit is given, right? So this is a very simple question. Directly we can get the answer. So I am leaving it to you. A rectangle of any size is selected from a rectangular grid of size 15 by 10 consisting of 150 squares of size 1 unit. The number of such rectangles with area an even number is. Here we have a rectangular grid of size 15 by 10. That means it consists of 15 multiplied by 10. That is 150 smaller squares of size 1 unit. Now we have to select a rectangle from this grid, right? Like this. This is one example. So this is one example. So there are many rectangles. We have to select one rectangle with the condition that the area of the rectangle is an even number. When will the area be an even number? Length multiplied by breadth is an even number. So either the length or breadth, one of them at least must be an even number. If both are odd numbers, then the area will be an odd number. So either the length or breadth or maybe both are even numbers, then the area will be an even number. So we will first find the total number of rectangles, right? So without any restriction, total number of rectangles. So there are 15 squares in any row, right? 15 squares. But to count the number of rectangles, we will not count the number of squares, but we will count the number of lines. How many vertical lines are there? There are 15 plus 1, 16 vertical lines are there. Similarly, 11 horizontal lines are there. To form a rectangle, we need 2 vertical lines and 2 horizontal lines. Let us select them. So there are 16 vertical lines. Let us select 2 of them. So how many ways can this be done? So that is 16 C2. That means from the 16 lines we have selected 2 vertical lines. Done. Similarly, from the 11 horizontal lines, let us select 2. So that can be done in 11 C2 ways. This is the total number of rectangles, but we don't want that. We want those rectangles which have the area even number. So that means you subtract all the cases in which the area is an odd number. Alright. So when will the area be an odd number? When both the length and the breadth are odd numbers, right? That is easy to subtract. Just one case, both are odd numbers. So subtract the cases in which the length is an odd number, breadth is also an odd number. When will the length be an odd number? We have to select 2 lines, vertical lines. Suppose you are selecting one of the lines, say 2. The number is 2, right? Now we have to select the next number. Say for example, the next line selected is 5, right? 5th line is selected. So this difference must be an odd number. 5 minus 2 is an odd number. So when will this happen? See, one line selected is an even numbered line. For example, 2 here. The other line selected must be an odd numbered line, right? So 2 and 5. Similarly, 3 and 8, whatever, one line must be an even numbered line. The other line must be an odd numbered line. But how many even numbered lines are there? Totally we have 16 lines, out of which 8 are even numbered lines and the remaining 8 are odd numbered lines. So out of these 8 even numbered lines, we have to select one of them. So that is 8C1. One even numbered line is selected. Similarly, the other line must be an odd numbered line. So 8 odd numbers are there. So 8C1. So that is done. Vertical lines are selected. Now horizontal lines. So how many horizontal lines? 11, out of which we have to select one of the lines, even numbered one, the other one odd numbered one. Same idea. So how many odd numbered lines are there? Totally we have 11 lines, out of which 1, 3, 5, 7, 9, 11. So there are 6 odd numbered lines. So out of which we need 1. So 6C1. Similarly, and even numbered lines, only 10, right, up to 10, 10, 8, 6, 4, 2. These are the odd number, even numbered lines. One of them we have to select. So that can be done in 5C1. So what is this? This is the total number of ways to select one rectangle whose sides are odd numbers. When will the sides be odd numbers? The 2 lines selected, right? The line selected, 2 horizontal lines selected, one must be an even numbered line, other must be odd numbered line. Similarly for the vertical lines. Okay, done. Alright, then just do the calculation, you will get the answer. That's it. So 16C2. So that is 15 multiplied by 8. So this is 11 times 5 minus, okay, this is 8, 8, 6, 5. So that's all. Let us do the simplification. We can take out the common factor, 8 multiplied by 5. 15 multiplied by 11, so that is 165 minus, so this is so 5 times 8 is taken out, so that is 48. So that gives you the value 40 multiplied by 165 minus 48, so that is 117. So if you do the multiplication, so we'll get so 40 multiplied by 170, so that is 4680. So that's all. So that is the required answer. So it's a very simple question, right? We have to select a rectangle satisfying certain condition. This is the direct formula you're supposed to know, right? So for a rectangle, to select a rectangle, we have to consider the lines, vertical lines. We need to select 2 vertical lines, 2 horizontal lines. That is done this way. From this, we remove all the cases which do not satisfy our condition, right? Which means odd sides are odd numbers. So that is subtracted. The remaining, we have even sides, right? One of the sides is an even number. That means the area will be an even number. So that is the answer. Consider a rectangular grid of size 8 by 6. One of the squares of size 1 by 1 is darkened as given in the figure. Find the number of rectangles and squares which do not contain this black square. Here again we have a rectangular grid. From this we have to choose a rectangle that does not include this particular black square. One of these small squares is black in color. We have to select all those rectangles which do not include this particular square. This question is similar to the one that we have done previously. You can try it on your own. Now you also have to find the number of squares which do not include this particular square. We have a general formula to count the number of squares in a grid of size n by m. So that is n multiplied by m. That is the total number of squares of small size. The next bigger size, that is n minus 1 multiplied by n minus 1. Similarly, m minus 1 multiplied by n minus 1, etc. until we get 0. So this is the general formula to count the number of squares in a grid. But here we only want those squares which do not include this particular square, right? So that question is also for you to think about. Alright, yes. With that, we'll wrap up our session on some random questions on permutation and combination. Until we meet again, bye for now.